Hello, my name is John Lee, and I'm the president of Alpha Training and Consulting. And I have a true passion for preparing students for ASQ certification exams. But today, what we're going to be doing is we're going to practice exam questions for the ASQ CCT exam, that Certified Calibration Technician exam. We're getting those questions right out of the CCT primer, which comes from Quality Council of Indiana. They gave us permission, very kind people out there, gave us permission to use the questions from the primer in this video. So thank you, Quality Council of Indiana. What a great group of people there. They also create a great product. We use this primer in our online class. What we have you do is listen to all the lectures, then review the primer, and we go over all the test questions with you at the end of each of those chapters. And that's what we're going to go over today. We're just going to do one or two questions from each chapter to give you a flavor of some of the exam questions that they may ask on the certification exam. If you're interested in that class, just go learning more about that class, just go to www.asqcct.com. That's ASQ Certified Calibration Technician, CCT.com. And hopefully you'll go check that out and learn more about our class. But for right now, what we're going to do is we're going to begin lecturing on those exam questions. So let's get started. Hopefully you'll learn something new through this. Have a great one, and I'll talk to you soon. All right, here we are at question 22. Carl Sagan, on his television series, might have said, quote, "Thank you for spending these billions and billions of nanoseconds with me," end of quote. How long a time interval is 18 billion nanoseconds? Note, use the U.S. definition of billion, which is 10 to the ninth. Okay, this is just a unit conversion problem. Let's go to the whiteboard and work this one out. All right, here we are at the whiteboard. Notice I've written down the information. I have 1,800 billion nanoseconds. So there's my 1,800. A billion is 10 to the ninth. So I put that there. That's the number of nanoseconds that he talked about. And I need to convert that over to seconds first. Well, how many nanoseconds are in a second? Or in other words, if you have a seconds per nanosecond, here it is, the conversion is 1 times 10 to the negative ninth is seconds per nanoseconds. So we're going to multiply these two together. That'll cross out nanoseconds and leave us with what the units we want, which is seconds. Now, the important thing is you have to know where to get this. 10 to the ninth nanoseconds, negative ninth seconds. What does nanoseconds mean? It's in your primer, and be sure and look that up. I didn't pull that out for this question, but I want you to go to your primer and make sure you can find that table. Remember where we went to giga and all that and found out there was more than 1,000? That's the table I'm talking about. Make sure you know where that's at and you're comfortable with it. That's where I got this 10 to the ninth for a billion, and that's where I got the 10 to the negative ninth for nanoseconds. Okay, let's multiply those out and see how many seconds that equates to. And first I'm going to clear it. Remember, to clear it, I usually just turn it off and on. And then I'm going to go, the way you put it in your calculator is you take this 10 to the ninth first. So I'm going to go 9, put that in. Then I'm going to hit second function, and this above the log, it's 10 to the x. So that will make it 10 to the ninth. So I put in 9, that will be my exponent. Then I'm going to go second function and hit the log button. And that converts it to 10 to the ninth, which we know is a billion. And then I'm going to multiply that times 1,800, times 1,800. And that's too big of a number, so it puts it in more of engineering type notation. And it's 1.8 e to the 12th then, if you want to look at it that way. Then I'm going to multiply that times 1 times 10 to the negative ninth. Now 1, I don't have to worry about multiplying because 1 times anything is that number, so I'm not going to worry about that. But I'm going to enter 9. Then I'm going to make it, guess what? I forgot to put times, I'm afraid, so I'm going to do it again. 9, second function, 10 to the x, times 1,800 equals, then I'm going to go times, I may have done it last time, but I don't remember doing it, so I'm doing it over, times 10 to the negative ninth. So I'm going to go 9 I'm going to make that negative by hitting this toggle right here. It'll change it from plus to minus. See, if I hit it once, it takes it to minus. If I hit it again, it'll take it to plus. That's why I call it a toggle. Toggles back and forth from plus to minus. I want mine to be minus. Then I'm going to go second function and hit the 10 to the x again. And it gives me the value of 10 to the negative 9th. Then I'm going to go equals. And it equals 1800. So that means there's 1800 seconds. 1,800 seconds. Very good. Now the units were not, the answers were not in seconds. So I'm going to convert this over to minutes. And I'm going to do that by simply taking my unit conversion, that there is 60 seconds per minute. And I want the seconds to be in the denominator. So 1 over 60 seconds. 1 minute. That will cancel the seconds and leave me with my minutes. So 1800 divided by 60 equals 30. So that gives me 30 minutes. Equals 30 minutes. Which of course is a half hour, and I believe that's the units they gave us the answer in. Let's go back to the blue page and make sure that's one of the options. So here we are back at the blue pages. Notice question 22, we had 30 minutes, which is a half hour, and that is the correct answer, B. All right, what ratio of attenuator would be required to reduce a 1 milliwatt signal to a 1, and I have to look up and see what F means, femto signal. So they could put whatever they want in here, but they're looking for a ratio of these two numbers, 1 milliwatt and 1 femto watt signal. And so that's only two numbers you need to worry about. So what I'm going to do is get the page out of the primer, which you should be pretty comfortable with now, or at least getting comfortable with it. It's 2.7 multipliers, and it has all these names of the numbers, deca, symbol DA, 10 to the 1, hecto, 10 to the 2, of course you know kilo, 10 to the 3rd, etc. So you're going to be using that quite a bit in the test, so be sure and get comfortable with it. Now, but I'm looking for M and F, so I'm going to have to come over here a little ways. And there it is, right there. There's M is milli, which is 10 to the negative 3, and femto, F, is 10 to the negative 15th. So that's all we need to do is get our calculator out. There we go. Of course, I covered up what we're looking for. But remember, milli is 10 to the 3rd. So I'm going to put that in first, 10 to the negative 3. Remember, milli is 10 to the negative 3. So I'm going to go 3 negative. Then I'm going to go second function and hit that 10 to the x. You've seen that before. And that will give me 10 to the negative 3 is 0.001. Okay, now we need to look for femto, which is 10 to the negative 15th. So I'm going to go divide. By the way, on this calculator, if you can't remember if you hit divide or not, it doesn't hurt anything to hit it again. So I'm going to go 15 negative. Then I'm going to hit second function 10 to the x again. Then I'm going to go equals. And that gives me 1 times 10 to the 12th. Okay, so let's go back to the question. So here it is, back at the question, 231, and notice there is one with 12 zeros, 3, 6, 9, 12. So 1 to the 12th times 10 to the 12th to 1. So the correct answer here will be D. That's pretty easy as long as you know where to get that table from. All right, 234. A client has submitted a 0 to 250 foot-pound plus minus 5% of full-scale torque wrench to a lab for calibration in the clockwise direction. That's the way it is. They usually calibrate it in the direction it's being used. That makes sense. The lab's 0 to 600 foot-pound, 0.25%, which is much better than this one, of reading clockwise and counterclockwise, the electronic calibrator, is out of order. Okay, so we're out of luck there. The lab also owns a spring and needle torque clockwise calibrator that is working and is in calibration. However, it is 0 to 1,000 foot-pounds, 1% of reading at 2 foot-pound. So can this calibrator be used instead? Okay. And this has to do with what we call TAR. And when you're comparing instruments and deciding if it's okay to use a substitute, there's this thing called TAR, Test Accuracy Ratio, by the way. And the rule is if it's 4 to 1 or greater, you can use it. So we need to calculate TAR. Again, that's Test Accuracy Ratio, Test Accuracy Ratio. So we're going to put the one being calibrated in the numerator and the one used for calibration in the denominator. That is the ratio they're talking about. So let's go to the whiteboard and work this out. All right, welcome to the whiteboard. Here we are, TAR. Remember, that's Test Accuracy Ratio, and we need to make this, if this ratio is 4 to 1, we're in good shape. Now, how do we do that? Well, this is the used less accurate instrument. Okay. Remember, we're going to test that to 250 foot-pounds at plus minus 5%. By the way, plus minus 5% is a range of 1%, so we'll actually be multiplying this by 1%. And this is the calibration instrument. Remember, it went to 1,000 foot-pounds, but we're only going to use it to 250 foot-pounds, if you'll recall. And that's 1% of gauge reading there, and plus the 2 feet. So we got that right out of the test question. So let's go ahead and do that. 250 times 0.1 is 25. So that was so easy, I didn't need my calculator, so I just wrote it down there. Now let's do the denominator. 250 times 0.01 equals 2.5 plus 2 equals 4.5. So it's going to be 25 divided by 4.5. So let's do that. 25 divided by 4.5 equals 5.5 to 1. So the TAR on this is 5.5 to 1. And that's over 4 to 1, so at least on the high side of the instrument, this is an acceptable substitute per the TAR rule of 4 to 1. All right, now we're going to do the same thing, only we're going to do the lower end range. And they didn't give us a lower end range, so I'm just going to say 50 foot-pounds. That's pretty small torque. I'm going to make that the small range, and just to see what we get. So we go 250 times plus minus 0.05. We already know what that is from our last calculation. It equals 25. Divided by 50 foot-pounds. 50 times 0.01 equals plus 2. And that gives us 2.5. Then we go 25 divided by 2.5 equals 10. So this is 10 to 1 on the lower end of the reading, 10 to 1. Both are, you may not have even had to do the lower range. We could kind of figure out it was going to be better. But both are above 4 to 1, which remember is the requirement for using a calibration instrument substitute. So there we go. That's how you solve that one. So yes, we can use it. Let's go back to the test question and see if we can find the correct answer. So here we are back at the blue pages, and we know it's a yes, so we can skip A and B. Yes, it is adequate for this job. Yes, it is adequate for this job, so I'm sure it's going to be C. Let's read D. Yes, because substitution of standards is almost always... No, you don't do it just because of that. You have to calculate it out, make sure it meets the standard. So the correct answer is C. If a 100-watt light bulb is on for 8 hours, how many joules will be consumed? All right, very good. Well, first of all, you have to know what a watt is, and it is a derived SI unit, but it is joules per second. Joules per second. So if you want to convert it into joules, you multiply it by time, and then the seconds will cancel out. Remember, watt is joules per second. Second in the denominator. So we'll have to convert hours into seconds and then multiply it by that 100 watts, and that will give us joules, which this question is asking for. So let's go to the whiteboard and work this one out. All right, so here we are at the whiteboard, and there's our 100 watts, which remember is joules per second. And there's my 8 hours, and I have to convert hours into seconds. So there's 3,600 seconds in an hour. So let's start canceling units out here. The hours are gone. The seconds are gone. And what are we left with but joules, which is the answer we want. So now we just have to multiply this through. Put my calculator up there, make sure it's cleared. I always turn it off and on just to make sure. Then I'm going to go 100 times 8. 100 times 8 equals 800, of course, times 3,600. Times 3,600. And there it is. It's going to be 2,880,000 joules is the correct answer. So let's go back to the blue page and see if that's one of the options. All right, here we are back at the blue pages, and remember it was 2.88 something, 2.88. So either it's going to be one of these two. We just have to pick the right units, mega, or I think uppercase G is giga. I'm sorry, uppercase G is giga, yes. And but remember, this was 2,880,000. And so we're looking for 10 to the 6th, which is mega. Giga is 10 to the 9th, I believe. Yes, it is. Yes, it is. So the correct answer here will definitely be C. So here we go. 3.1, separating the variation of a measurement process into each of its individual influences can be done with a gauge separator? No. A measurement capability study? Yes, probably. A gauge R&R study? Good, but not as good as B. Let me explain. The gauge R&R study splits it into repeatability, reproducibility. Those are the only individual components it breaks things into. And reproducibility, environments put in there, not everything else kind of put in there, but we still say it's operator to operator. Measurement capability study, on the other hand, is much more thorough. Uses DOE principles, uses the ANOVA specifically, and it can break it into repeatability and reproducibility, but it also separates it into environment, traceability of the chain of standards. So it's a more complete answer, B is. Now, if it would have said breaking it into its individual repeatability and reproducibility, we'd go with the gauge R&R study. But with that not being said in the question, then we're going to go with B, a measurement capability study. Then it talks about an uncertainty budget, but the uncertainty budget is where we record all the uncertainty values in the breakdown of all the different components, and we break it into percentages and those types of things. So the uncertainty budget is like the final report for uncertainty. So the correct answer here is no doubt B. A technician is calibrating portable truck scales and works mostly outdoors. Okay. He or she carries an open clipboard with data sheets for recording results. Good. This describes a condition that is acceptable, okay, I don't know, to be honest with you. It could be acceptable. Right off, I didn't see anything that they really did wrong. He or she carries an open clipboard with data sheets. Okay. Unacceptable because the data are not being recorded in a computer? No, it doesn't have to be recorded in a computer. Acceptable because the data are not protected from the elements? Yeah, that's probably it. It could rain and cause all kinds of problems. And it does say specifically she carries an open clipboard and she's outside. So I imagine C will be the correct one. Unacceptable because the data will not be legible. We don't know that. But C is the best answer. It's not protecting it from the elements, and they're working outside. So 3.5 is at C. I'm going to have to look again, but I felt fairly confident, and that is the correct answer. Here we are at question 21, a reference standard long gauge block, a dimensional standard, made of gauge steel, has been traceably calibrated at ISO standard reference temperature and is exactly 100 millimeters long. Okay. What error will be caused if this same block is used at 30 degrees Celsius and thought to be of the same length? So what they're going to have you do here is there's a change in temperature. And the change in temperature is going to expand this gauge steel. And so we have to do a mathematical calculation to figure out what that is, which means we need to go to the whiteboard. All right, here we are at the whiteboard, and this is the information I have. I looked this up. This is the expansion rate of that gauge steel, 11.5 parts per million per degrees Celsius. So you'll have to look at what does part per million means, a millionth of an inch, or whatever unit we're using, meters, I guess. Okay, millionth of a meter. And the change in temperature was 10 degrees Celsius. By the way, what page do you look for these numbers? It's going to be around, let me see what that is, around page 14 of chapter 4. We'll give you an example of this problem and where to find those numbers. Okay, and the change in temperature was 10 degrees Celsius because the standard for calibration lab for temperature for dimensional measurements is 20 degrees Celsius. This one was at 30 degrees Celsius, so it's 10 degrees warmer. Okay, so the change in length equals that expansion rate coefficient there, and I forgot to put the degrees Celsius in there, and I don't have room, so remember it should say parts per million per degree Celsius, just like this one, times 100 millimeters times 10 degrees Celsius. This Celsius will cancel that Celsius out, and we're left with a millionth and a millimeter there. And anyway, you multiply all those out, and it ends up being 11,500 nanometers, or 11.5 micrometers, which is 10 to the negative 6 there. And that's how you do this problem. They're not overly difficult. The most difficult one is, keeping your units correct. So anyway, let's move on to the next question. All right, here we are at question 25. If during calibration the technician finds that the unit is out of tolerance and it can be adjusted, he or she should. Who is this? Technician, the calibration technician. Well, for heaven's sakes, that's what you're there for, is to calibrate it. So attempt to adjust the unit, yes, obviously. Take the unit, notify the customer. No, you're supposed to calibrate it. Send the unit, no, it's not out of repair, it just needs to be calibrated. Return the unit to the customer without further work. No, what are they paying you for? Come on. No doubt, this one was an easy one. 25 is definitely A. All right, here we are at question 4. If a continuous process followed the exact distribution of the roll of a single die, what would be the standard deviation of the process? Okay, first of all, you must know that this distribution of a roll of a die, think of it, so you can roll 1 through 6. What's the probability of getting a 1? 1 in 6. What's the probability of getting a 2? 1 in 6. What's the probability of getting a 3? 1 in 6. Every one of them has the same probability. When the probabilities are equal over the range, that every event has an equal probability, it's called a uniform distribution. So that's the first thing you need to know. Then you need to find the formula for the standard deviation of a uniform distribution. So I'm going to pull up the page from your primer, page 64 on the revision I'm using. So they'll call that a rectangular or uniform distribution. So here it is, rectangular distribution. All the odds are equal. Okay. This is the normal distribution. Odds are high in the middle and the odds decrease as you go out. That's the normal distribution. Triangular is similar to the normal distribution, only it's linear, but probabilities decrease linearly as you move away from the average. Okay? This one isn't linear. Okay? And this is the U-shaped distribution. Notice probabilities are high on the edges and low in the middle. That's a U-shaped distribution. But regardless, this is the one we're interested in, and this is the formula. A divided by the square root of 3. What is A? It's the range. The range. Okay? And what was our range? 1 to 6. 1 to 6. All right, and that's good. So 1 minus 6 is 5. So this is 5. From negative A to A is 5. The whole spread is 5. That's the range between the whole numbers. We have to divide that by 2 to get A. That A is half the length right there. So we're going to have to go 1 minus 6 to get the spread, which is 5. Divide it by 2, which will give us 2.5. 2.5 divided by the square root of 3 will be the correct answer. So we have to put the bigger number in first, don't we? So let's do it correctly. 6 minus 1 is the range of that distribution, which is 5. So again, what does that mean? That means this distance between A minus and A plus is 5. Now, what do we need to do to get A? We need to divide that 5 by 2. So that's the next thing we do. 5 divided by 2 equals 2.5. Okay, now that we know what A is, we can go A divided by the square root of 3. So here we go, A divided by the square root of 3. So I'm going to go A, 2.5, and I'm going to hit the division sign, and then I'm going to enter 3 square root equals. And that is the value of the standard deviation, 1.44. Let's go back to the blue pages and make sure that's an option. All right, here we are back at the blue pages, and there's our option, 1.44 there, and that is correct. 511, what is the binary representation of 64? Okay, let's go. I'm going to take you to the primer, to a page that will make this pretty easy. So let's go ahead and go to the primer. All right, here we are at the primer. I'm on page 27 now of Chapter 5, and they have this binary table, and they want to know what 64 is. Well, if you put 1 here, that'll be 64. So it'll be 0, 1, 0, 0, 0, 0, 0, 0. Now, if they would have asked for 65, there'd be a 1 here and a 1 here, because that'd give me 64 plus 1. If it was 68, for example, I would go put a 1 here, 0, 0, 0, 1, 0, 0. And that's how it works. But this one's real simple. We'll have 1, 1, and the rest zeros. How many zeros? 1, 2, 3, 4, 5, 6 zeros. So let's go back to the blue pages and make sure that's an option. So we know it's going to be 1 with 6 zeros behind it. 1, 2, 3, 4, 5, 6, 7. No. 1, 2, 3, 4, 5, 6. Yes, the correct answer is B. Add the following angles: 123 degrees, 53 minutes, 33.1 seconds, plus 104 degrees, 21 minutes, 14.1 seconds. So we'll go get the calculator and we'll work through this one. All right, here we are at the calculator. I'm going to go ahead and enter in 123 degrees, 53 minutes, 33 seconds. It won't put 33.1, so I'm going to have to add those in after I'm finished. So let's go ahead and do that. 123.53. Now, many students ask, well, what if it's a single digit? Then let's say it was 3 minutes. Then you'd put 03 right there, just so you know. And then I'm going to put in 33. And the calculator will read this as 123 degrees, 53 minutes, 33 seconds. Now, I'm going to go down, I'm going to convert this degrees, minutes, seconds into decimal degrees. And I'm going to do the same thing for that 104 degrees, 21 minutes, 14 seconds. and I'm going to convert them both into decimal degrees. Then I'm going to add them together. Then I'm going to come back and I'm going to convert from decimal degrees to degrees, minutes, seconds. Okay, so let's go ahead and move forward here. Let's go second function and then hit DMS to DD. That's converting it from degrees, minutes, seconds to decimal degrees. So we'll just work in degrees, but it'll be decimal format. So let's do that. Second function, there we go, and DMSDD, which is right above the plus sign. And that means 123 degrees, 53 minutes, 33 seconds equals 123.8925 degrees. And you may ask, why don't you just work with that anyway? That's a good point, I think. But lots of times you'll see these on drawings. All right. Now that we have that one, I'm going to go plus, hit the plus sign, because we're going to be adding these together. Then I'm going to go 104.2114. There we go. Then I'm going to go second function, degrees, minutes, second to decimal degrees, and 104 degrees, 21 minutes, 14.1 seconds equals 104.3538889 degrees. Now I'm going to go equals, and that added the two together. So I know it's going to be 228 degrees something, so I know it's either A or D already. But we'll make sure. We're going to hit second function, decimal degrees to degrees, minutes, seconds. So we're going to convert it back now. And it's 228 degrees, 14 minutes, 47 seconds. Okay, so it's either A or D. We already knew that. And notice I didn't add these decimals, but 0.1 plus 0.1 is 0.2. It's not 0.11. So D will be the correct answer. Let's go back to the blue pages and solve some more problems. 6.4, uncertainty is. Okay, remember, uncertainty is standard deviation or variance. A modern method for quantifying measurement variation. Yes, it is that. A collection of tools and techniques for measurement. No, it has to have variation in there because that's what uncertainty is. A modern tool for identifying quantities that influence a measurement. No. The current international variation standard. No. The best answer here is A, and that is correct, no doubt. Let's move on to question 5. All right, here we are at question 9. The standard deviation of a rectangular tolerance of x plus minus a can be expressed as, so the rectangular tolerance, and I'll take you to the page 64 of your primer. And here it is, rectangular, standard deviation equals a divided by the square root of 3. You're going to need this page quite a bit on the test, so make sure it's marked and you can readily retrieve it. All right, let's go back to the blue page and make sure this is an option. And there it is, it's C. So now we can move on to question 10. When calculating an uncertainty budget, an example of a type B component is what? Well, remember, type A, you're running an experiment, you collect data, you do a lot of analysis, and etc. Type B calculation, you just get a number and divide it by the square root of something. So, variance determined from replicate experiments with 2 or more people? No, that is type A. The value from a calibrated certificate? Yeah, you find the value, you divide it by some square root number to get it, type B calculation. So B is going to be correct. ANOVA data, which quantifies random effects in measurements? No. ANOVA is definitely a type A. The standard deviation of a normal distribution of instrument repeatability? No, repeatability is usually a type A type calculation. So the only one that can be type B is answer B. Let's move on to question 11. The prime use of a control chart is to detect assignable causes of variation in the process. Yes, that's the objective of control charts. So you need to remember that. They test on that all the time. But I'm going to read on to make sure that we have nothing else going on here that could be a better answer, although there's not much better than that one for the definition of the objective of SPC. Detect non-conforming product? No. You don't even know where the spec limits are necessarily when you're plotting on an SPC chart. And besides SPC, you plot averages, not single events. And when you compare averages to the spec limits, that's a worthless comparison. You need to remember that. You don't try to determine capability with SPC because SPC uses average, and per the central limit theorem, that squeezes everything down. So, in short, don't compare control limits to spec limits. Okay. Detect non-conforming product. Measure the performance of all quality characteristics of a process. No, number one has all. That's an absolute. Detect the presence of random variation in the process. No, its main objective is to detect assignable causes. So 7.2 is definitely A. The primary reason that non-conforming material should be identified as segregated is to do what? To keep it from being used in the process, so that the cause of the non-conformity can be determined. No, the primary reason for segregation is not to determine the cause of non-conformity. That may take place in the MRB team or something. So it cannot be used in production without proper authorization. That will be the correct answer. To obtain samples of poor workmanship for use in the company's training program. No, that's not the primary reason. So that responsibility can be determined and disciplinary action taken. No, that will never be correct on something that's looking for a positive response on a test question in ASQ. They do not like you punishing people for system problems. So it's going to be B. 7.10 is definitely B. Let's move on to question 11. All right, congratulations. You've finished this video, or almost finished this video. If you have any questions concerning ASQ certification exams, please contact me. As you can see, I've passed most of the ASQ certification exams. You can contact me through my website at alphatc.com and go to the Contact Us option and send me a message. I'd love to hear from you, and I'll get back with you as soon as possible. Thank you, and have a great day. Goodbye.